Good afternoon, students. We will be doing today IR spectroscopy. Okay, and today we will be covering a part of it only, and it will cover almost up to fundamental to the positions of O, and sulfur containing functional groups. Okay, that will be our syllabus today. So, what is IR spectroscopy? IR spectroscopy is the molecular phenomena that is shown by the molecules after absorbing the infrared electromagnetic radiation. By using this IR spectroscopy, we can identify any functional group transformation very easily. See, for example, here the ketonic group has been reduced to alcohol and it has changed to CHOH. So this functional group transformation can be easily identified, and also we can identify several others. Another example has been cited here. Nitro is converted into NH2 amine. Okay, so let's see the next one. So here, what is the radiation that is involved? The radiation that is involved, you can see we have started from low low energy to higher energy. Here we have UV visible also, visible, UV visible. So it lies near red light of visible. So therefore it is called infrared. Okay. So we have far infrared, which is very near to microwaves, middle infrared, and near infrared. Okay. So the region extends from 4,000 to 400 centimeter inverse. Okay, is of the interest of organic chemist, as most vibrational transition of organic functional groups occurs in this region. Okay, so here this is the higher energy, this is the lower energy. Here we have using the unit centimeter inverse, that is wave number. Okay, so centimeter inverse, we know h nu is the energy, and mu is equal to c by lambda, and c by lambda means it is centimeter inverse. So since c is constant, we are taking here 1 by lambda, and this is centimeter inverse. So therefore it is having a direct relation with frequency, and therefore we can tell it is of higher energy and this is of lower energy. Let us see the next slide. What is the use of infrared spectrum? Every type of bond in a molecule has a unique natural vibrational frequency. We will see it very elaborately. Therefore, the IR spectrum means the IR graph, or you can in simple words is the graph. Okay, IR spectrum of every molecule is unique as much as the fingerprint of human beings. So you can understand, you know it very well, that every human being has got their unique fingerprint. Okay, no fingerprint of any two individual will be similar. Okay, so similarly the IR spectrum of every molecule is different from that of a different molecule. It will be never similar. Okay, if it is the same molecule, two similar molecule may have same fingerprint region or same IR spectrum, but if the molecules are different, then maybe it is a very slight difference is there. But even though the slight difference, the fingerprint region or the IR spectrum will have a region which is called the fingerprint region, and it is very unique. Rest part may be similar, but a part which we call as a fingerprint region, mostly in the lower energy side. Okay, that part of the spectrum or the graph will be unique, and it will be not having any similarity with that of the molecule which looks to be very similar, but it is different. Okay. By comparing IR spectra or two samples, one can establish whether or not, they are identical samples. Okay, we can very easily identify whether the samples are similar, same or different. Okay, if their IR spectra exactly match, then they are likely to be same substance. Okay, if the IR spectra are almost similar, coinciding, the peaks are or in the same region or in the same locations, then they are having then they are the same substance. Okay, same molecule. Next is use of IR spectrum. Okay, absorption due to vibrational spectrum of vibrational transition. There is a transition. You have studied electronic transition. Now you will be studying vibrational transition. In every vibrational transition of each bond, now every bond has a vibration. Okay, all the bonds are vibrating just like our you can say the spring. Okay, a spring, just like a spring keeps on vibrating, the every bond keeps on vibrating. Okay, so absorption due to vibrational transition of each bond type is different, and they are confined to a small portion of the IR region. Supposing OH, it is a bond and it will vibrate. Where it will lie? It will lie in the region 4000 to 2500. NH similar position, CH similar position. Now say for example C triple bond C, C triple bond N. Okay, and just like that O double bond, C double bond O, C double bond O, C double bond O, C double bond N, something like that. Okay, this will lie in this region. Then metal carbonyls. Okay, metal carbonyls, you have read organometallics. So these also give a vibrational frequency in the region 2000 to 1800. So whenever we see a peak is there in the graph which is in between 2000 to 1800, we are definitely sure that it is a organometallic complex. Okay. Similarly, 1800 to 1650, it is typically for ketones or aldehydes or any type of C double bond O. 1600 to 1650 to 1550, it is C double bond C, C double bond N, N double bond O. Okay, and 1550 to 650. See, this region is called fingerprint region. So I told you it is towards the lower energy side. So this lower energy side is fingerprint region, and it is all due to single bond between carbon and some other atom. Okay, it is between carbon and some other atom. If it is between carbon and hydrogen, it is not in the fingerprint region. Okay. This allows identification of functional groups in the organic molecules because each functional group has a vibrational frequency which appear in a narrow region of IR region. Okay, so we have now learned all the various common type of functional groups stretching vibrations. Okay, so let us see the next slide. So vibrational frequency can be of now we are studying molecular vibrations. Molecular vibrations can be of two types: fundamental vibration and non-fundamental vibration. Fundamental vibrations can be again of two types: stretching vibrations, bending vibration. Stretching can be two types: symmetric stretching, asymmetric stretching. Bending can be of two types: in-plane bending, out-of-plane bending. The in-plane bending can be of two types: scissoring, rocking. Out-of-plane bending can be of two types: dragging and twisting. Non-fundamental vibrations are of different types like overtones, combination, tones, Fermi resonance, etc. Let us see the next slide. Now, what is fundamental vibration and non-fundamental vibration? Vibrations which appear as band in a spectra is vibration, the fundamental vibration. Whatever bands we see in the spectra is fundamental vibration. Non-fundamental vibrations, the vibrations which appear as a result of fundamental vibration. Okay, as a result, like in a pond, when you throw water, throw a stone on the water surface, there will be some kind of ripples, or you can say the vibrations will be there on the water surface. Now, whenever this water surface, the fundamental one is the first one due to the stone, and due to the first one, when there will be the next wave or next vibration coming out of it, it is non-fundamental, because it is not coming due to the stone, but it is coming due to the first, wave that was created by the stone. Okay, so that is what is non-fundamental. Now, stretching vibrations, fundamental vibrations can be of two types. We have told it: stretching vibration and bending vibration. What is stretching vibration? Stretching vibration involves continuous change of interatomic distance along the axis of the bond between two atoms. Okay, so we will see stretching vibration is always of more energy than that of bending vibration. And bending means whenever there is a characteristic vibrations are characterized by a change in angle. Whenever there is a change in angle between two bonds, okay, there should be two bonds, and it is called bending vibration. So let us see this. Supposing, what is this? The stretching vibration can be of two types: symmetric vibration and asymmetric. You can see here both the bonds are lengthening and shortening similarly, symmetrically. Okay, so therefore it is called symmetric vibration. Here, see asymmetric vibration. One bond is shortening, another bond is lengthening. So therefore it is asymmetric vibration. Let us see the next one. Now it is bending. Bending also is of two types. I have told you already. In-plane bending. Now what is in-plane bending? Here, if you see, all the three atoms are on the same plane. And what it is happening? Both the atoms which is bonded to this yellow atom is coming together to the same point and then again moving away. So it looks more like a scissor. So it is called scissoring. Here you can see rocking. What is rocking? The both are what? There is no change in angle, but both are going away in one side and then again coming to the other side. So they are simply rocking. You can say if you take the word rocking chair, so that is rocking from one pole to the other pole. Okay, out of plane. Now here see what is this happening. Here two atoms are coming out of the plane, okay, towards you, then again moving away from you at the back of this plane. So therefore they are not in the same plane. Therefore, what is the change? Change in angle between the plane of a group of atoms. Okay, so these two atoms and this atom, there is a change in the plane of these two atoms. Okay, the twisting. Now twisting, what is this? Here we have a plane here and this is another plane. These two planes are continuously changing its angle. So here one is coming towards you, another is going away from you. Okay, so therefore it looks more like a twist. So it is called twisting. So coming together, it is a linear molecule. This is a linear molecule where we have taken carbon dioxide. It is symmetric stretching. It is asymmetric stretching. You can see one bond is lengthening, another bond is shortening, and this is bending. This is what? One is going out of the plane and another is going up the plane. Okay, and down the plane, up the plane. So therefore it is bending. So we have seen all this. So let us see next one. Here what do we get? Okay, we will discuss this in our next video.